Oops. Okay. Go.
Okay. To begin with, let's recall the setting for the plateau problem. We have gamma, some smooth closed curve in our fluid. We define M to be the complement of gamma, and all of M is the real line bundle over M, which in a certain sense detects all of the boundary components. This is the bundle which Marco introduced in his talk. So this is non-trivial. Line bundle, and the characterizing property of L, say this is our curve gamma, possibly with some connected components, possibly interlinked. Then if I take any small loop which links one of the boundary components with winding number 1 and doesn't link the other one, then this will be a generator for the homology, and the bundle restricted to this curve is the Mobius bundle. Okay. And in particular, any section of this bundle has to have a 0 on such a curve, because if it starts here, it needs to end here, and so it has to cross 0 at least once. And if it only has isolated zeros, then there'll be an odd number. Okay. This is our bundle.
So you can have an interval of zeros?
Yeah, that's right. I mean,
no problem.
Yeah.
Yeah, generically. Yeah, generically for sure.
Okay, so now let's consider section U. It solves the Allen-Cahn equation. U solves this PDE, which means that it's a critical point for the energy the Allen-Cahn energy on the space of sections. So the focus of the talk today is going to be about solving the plateau problem using this framework. But first I want to just quickly finish the discussion we were having yesterday about the monotonicity of the rescaled energy in balls, because this will play an important role in the analysis today. So Marco used the first variation formula to compute how the rescaled energy is changing as a function of the radius. And the important part of the computation for us is that this difference is bounded below by some integral involving the discrepancy.
Maybe 3.
Thank you. So we almost have monotonicity, but there's some kind of error term here. If the discrepancy is positive in some places, then this integral will be negative, and so we don't quite get the monotonicity that we want. But what I want to convince you of is that as we send epsilon to 0, this term here becomes non-negative. So although we might not have monotonicity for positive epsilon, in the limit, the energy ratios become monotone. And so what we need to establish is that the positive part of the discrepancy is going to 0 in L1. That will be sufficient. And we started to give the argument yesterday. So we need to combine two estimates for the discrepancy, one away from the boundary and one close to the boundary. So let's first recall the interior estimate. So it's going to be convenient to define a function rho of x. This is the distance from x to the boundary, gamma. Then what the interior estimate says is that if we're at a point x, where the distance to the boundary is at least like some large constant times epsilon, okay, then we have enough room to introduce a cutoff function and exploit the elliptic equation for the discrepancy to prove a suit bound by the maximum principles. And that estimate looks like discrepancy less than or equal to a constant times epsilon to the 1 minus q, where we're thinking of q as being very small. And this constant c depends on lambda, q, and an upper bound for u. We can't expect such a nice end near the boundary. In fact, we argued that even for the nicest possible solution, the boundary model, whose nodal set is a half plane, the discrepancy actually blows up at the boundary. But we can prove an estimate controlling how fast it blows up. So, on the other hand, if we look at a point x where the distance to the boundary is less than some constants, lambda times epsilon, then what we see is that the discrepancy is bounded by c over x. And now c just depends on lambda and an upper bound for u. And yesterday I indicated how to prove this over a punctured ball in R2. And the proof here is very similar, uses very similar ideas. This is my curve gamma. Then I can look at a segment of gamma and take a tube around that segment, like this. And up to an appropriate choice of coordinates, this tube is identified with two-dimensional ball of radius r minus the origin times an interval. So I can write points in this cylinder over the punctured disk at ZP, and again, lift the section U to a double cover of this punctured cylinder via the map which acts by the complex square in the first component. And then exactly as we saw yesterday, the section lifted to the double cover becomes some function which is odd in Z, and it has a singularity along the segment Z equals 0, but the singularity is removable.
Even on the second.
That's right.
Is it standard?
I think what's important is that the singularity is codimension 2.
Okay.
And that we have a bound on the W12 one. So these are the crucial things. If it was larger, if the codimension was smaller, you would have a problem. But codimension 2 is fine. Yeah. So you can lift it, fill in the singularity, and then you get a smooth solution to a nice elliptic equation upstairs. And you can apply elliptic regularity to get derivative bounds for that function. And rewrite those estimates in terms of the section. This is the estimate you get. And the fact that you have this blow up, like 1 over the distance, this is inevitable because the Jacobian of the complex square is going to 0 as z goes to 0. Okay, so hopefully this discussion and what we did yesterday in the lecture is enough to convince you that this estimate is reasonable. Great. So with these 2 estimates in hand, it's quite simple to show that the positive part of the discrepancy goes to 0 in L1. So I'll quickly do this computation and then we'll move on to the Plateau problem. So if we take a compact set K in R3 and integrate the discrepancy over K, we're going to want to split this into a piece close to the boundary piece that's away from the boundary, and rewrite the first term using the co-area formula. This is the integral of 0 to vector epsilon. Then we integrate C over the level set rho equals T.
Are they gradient?
Well, rho is a distance function, so the gradient. Good. Okay. And now I simply input my estimates. So on this level set, C is like 1 over rho, which is 1 over T. So the first term I can bound by let's call it, this is the area. I should intersect with K here, of course. This is the area of the cylinder where rho is equal to T, intersect with K. With a constant C. And here, just bound this by C times epsilon to the 1 minus Q. And then let's just be crude about it. Take the volume of K. Now let's think about this. This is a cylinder of radius T. So the area is of order T. So that cancels the 1 over T. When we integrate, we're left with a constant lambda times epsilon. Times this term of order epsilon to the 1 minus Q. And so as epsilon goes to 0,
Because Q was
smaller than 1.
okay.
Yeah.
Okay.
Yeah. So remember on the closed manifold, we've got epsilon to the power 1. So what this is saying is if you're working locally, you get an estimate which is almost as full. So we think of the Q as being very, very small. Great. Let's turn now to the plateau problem. The assumption now is that our sections U actually minimize the energy. And in this case, we claim that as we send epsilon to 0, the nodal sets accumulate around a section of a solution of the smooth plateau problem. Let's first record some basic properties of the minimizer. So the first thing that we can say is that U is bounded from above by 1. And why is this true? Well, if not, then I can construct a competitor with less energy. And how do I do this? I just look at any region where U is bigger than 1 and change U so that it's equal to 1 in that region. So then it's constant in said region. So the Dirichlet term will be 0, and W is smaller at 1 than it is at some value larger than 1. So this decreases the energy. So I take V to be U if at points where it's less than or equal to 1, U over absolute value of U at points where U is greater than 1, this will have less energy. And this is important because, in all of our estimates for the discrepancy, for example, the constants depend on an upper bound for U. So if we want to use those, then we need to check that U is bounded. We also know that the energy of U is bounded purely in terms of the curve gamma. Okay? It has a bound which is independent of epsilon. And how do you see this? Well, it's enough to find some section whose energy is bounded. Then we can, because U is the minimizer, we automatically get an upper bound for the energy of U. So what we want to do here is consider some smooth surface S whose boundary is equal to gamma, and construct a section whose nodal set is accumulating around S in such a way that the energy is nicely controlled. So then there exists a section V such that energy of V is very close to the area of sigma up to normalization. So this constant Q sigma is energy of the one-dimensional solution. How do you get this competitor V? Well, as Marco explained, we can pass to a double cover of M where the lift of S is separating, and then we can look at a one-dimensional solution composed with the sine distance function to the lift of S, and this will have this will do what we want. Okay, so I won't explain this in much detail. I'll just say consider the lift of S and double cover of M corresponding to our chosen line bundle. And the lift of our desired section V will be a rescaling of the one-dimensional solution composed with the sine distance function to the lift of S, where the signs are chosen so that you're positive outside S, negative inside, or vice versa. It doesn't. This will do the job. So, given these uniform bounds for U and its energy, what can we say already in terms of the convergence as epsilon goes to 0? The interior case, the behavior away from the boundary is well understood. Here, one should refer to the work of Monica Mortolo, more recent work by Wei. What we can say using their interior regularity theory is the following. As we send epsilon to 0, let me write this differently. Let's say there is smooth, properly embedded minimal surface sigma M, which importantly does not include the boundary at this point. And what we can say is that the 0 sets of our sections are converging to sigma locally in the graphical C2 alpha sense. So these converge to sigma. The graphical C2 alpha log. And there's one more fact which I need here, which is that we also have convergence at the level of the energy. So up to an appropriate renormalization, the energy of the sections converges to the area measure on sigma. So moreover, so I take the energy measure, which is just the density times the Euclidean volume measure, then this converges in the weak star sense after normalization by the energy of the one-dimensional solution. The two-dimensional Hausdorff measure restricted to sigma. Is that good?
Should we one over to sigma?
No, but I perhaps did it wrong here. Yes, I did it wrong here. Gotcha. Okay, so for us, what this means is that we're always working in balls. So if we control the energy in some ball, then we also control the area, and vice versa. So much for what we can say using the previous work of other authors. The new part is the boundary regularity statement. Using myself and Marco. And he simply says that sigma is smooth up to the boundary gamma. In fact, once you know this, it follows immediately that sigma viewed as a smooth surface with boundary has boundary equal to gamma. And it's also easy to see that sigma solves the Plateau problem. We've just grabbed boundary gamma. Yeah, there's one extra point which I would maybe mention already over here. Which is that we know that if we take the closure of sigma in R3, then the boundary gamma will be a subset. And this comes from the definition of the bundle. Remember, I said if you draw a little loop around one of the boundary components, any section has to vanish on that loop. So that means that the boundary gamma is always in the closure of the zero set of any section. Okay, and since the zero sets are converging to sigma, that automatically forces gamma to be in the closure of sigma. And in this step, it's crucial that we chose the bundle correctly. Right? If we chose some other line bundle, which fails to detect one of the boundary components, then you wouldn't expect that boundary component to be in the closure of sigma. Okay, so I think that's an important point. How the choice of bundle already forces sigma to span gamma in some sort of weak sense. Then the challenge is to prove that you're really smooth up to the boundary, because at this point we know gamma is in the closure, okay, but at some boundary point there could be many different things that are happening. You could have lots of pieces coming in like this, also pieces which are coming in such a way that they become tangent to each other. Then these almost tangential pieces could be joined by a sequence of little nets, so that the curvature is flowing up near the boundary. At this point, there's really a lot of possibilities until we carry out our analysis. Let me write here, what's the strategy? What we have to do is blow up at an arbitrary boundary point. And if we can show that the blow up is a single half plane, then the Allard regularity theorem tells us that sigma must be a smoothly embedded surface up to the boundary. So we want to show that the blow up at any boundary point is a half plane at which point we can apply the Allard regularity theorem. We're working towards, first of all, being able to blow up in the first place, right? Is this actually possible? And if yes, then what are the possible limits? So what we already know is that the area ratios of sigma are monotone at boundary points. And this comes from the almost monotonicity for the energy ratios, which was improving to a genuine monotonicity by the L1 decay of the discrepancy and the convergence of the energy to the area of the surface. So that's the first step. So let's consider a boundary point. And up to a translation, we can assume it's the origin. Then I should write it out. So, using the almost monotonicity for the energy.
The other term you are missing one term that's possible, right?
Yeah, I'm not going to use it, so I just throw it away.
That's so close to the limit, that term that you are missing, can make this positive, the whole value in the right hand side, or you also go to zero.
The term I threw away is manifestly non-negative. Doesn't.
No, but I mean, say this inequality, you say it's going to be bigger than zero. Then epsilon is close to zero.
Yeah.
So the other term, when it's very close to zero, this inequality is positive because of the other term, or the other term also goes to zero.
Well, no, I mean it could be positive or it could be zero.
You cannot control it.
I'm not sure what you can say,
Okay.
but I always just throw that term away.
I think if they're converted to a cone, which you could, you could convert to a cone when epsilon was to zero.
Yeah, that's it. You can control the other direction. I'm trying to beat this one.
That term will go to zero if the limit is a cone. Because the term is zero.
Yeah, that's true. Yeah, what I don't know how to show is if that cone goes to 0, then do you have to be a cone? Yeah, me neither. Okay, but we have this. Know that the positive part of the discrepancy goes to 0 and a 1. Okay, so using these two facts, we find that sigma intersect BR, of course. This implies a monotonicity for the area ratios of sigma. So if we consider a sequence of scales, Rk, which are convergent to 0, and we look at the rescaled surfaces. Okay, obtained by dilating sigma by 1 over Rk. Then this sequence of dilations has a uniformly bounded area in every compact subset of R3. I would like to argue that these rescaled surfaces converge in some sense. And a nice way to do this is to observe that, let me draw a picture. So we have some small ball, sigma maybe looks something like this, and it's obtained as a limit of nodal sets of Allen-Cahn sections. So if epsilon is very small, then we should see some nodal sets which are converging nicely to sigma. Now, when I dilate, the situation is, of course, the same. The dilated surfaces are still approximated by the 0 set of some minimizing Allen-Cahn section, right? Namely, let me call this section U hat of K, where U hat K of X is defined to be U of K times X. Okay. So for any fixed scale Rk, as I send epsilon to 0, the rescaled sections converge to my rescaled surface.
Do you have to rescale also in the form, like R to -2?
No, I don't think so.
Because when you do the Laplacian, you have to do R squared.
It won't solve the same equation. it won't solve the same equation.
Ah,
So now the but all it is it's essentially
so you're
changing
changing the
changing the epsilon.
epsilon instead of the. Okay.
Now the equation will be like this. Yeah, that's right. And so now so we're sending k to infinity and we're sending epsilon to 0. By taking an appropriate diagonal subsequence in k and in epsilon, I can argue that my rescaled surfaces they're converging to the same limit of the nodal sets along my diagonal sequence of sections. I don't know if I explained that in the best way, but hopefully it makes sense. So we want to pass through a diagonal subsequence such that Rk over epsilon still tends to infinity, right? So then this sequence of rescaled sections, they're still minimizers in their respective bundles. So the same interior regularity theory tells me that they converge in compact subsets. So I can arrange that the 0 sets of the rescaled sections converge to some limiting surface sigma hat, and as long as I also choose my subsequence such that these 0 sets are converging to the rescaled surfaces quickly enough, then they have no other choice but to converge to the same limit. So I also get that a rescaling of sigma converges to sigma hat. The graphical. So we have some blow up now. Dilated surfaces are converging to some sigma hat in an appropriate sense. So what is sigma hat? It's going to be some properly embedded minimal surface. Now the exterior of the blow up gamma, which is just R3 minus the tangent space at the origin. And there's something else I can say about sigma hat. Because on my original surface in sigma, I had monotone area ratios. The area ratios of sigma hat must be constant in the radius. If I look at the area of sigma hat, any ball around the origin divided by r squared, this will be equal to the limit as s goes to 0 of the area ratio of the original surface sigma. Of course, it's just some constant. The limit exists because the original surface, this is a bounded monotone sequence.
Can you repeat that, please?
Yeah.
So that's not because they were the formula, right?
That's right. So you agree that this limit exists and
Yes.
is some number. Okay. So if I take this, and of course sigma hat is some limit of these gains, right? So the area ratio of sigma hat in the ball of radius r will be like, it will be equal to, in the limit, the area ratio of sigma in a ball of radius on the order of rk, the scale factor. So as k goes to infinity, these balls shrink to 0. Right, so sigma hat has constant area ratios, and it's then a consequence of the usual monotonicity formula for minimal surfaces that sigma hat has to be a cone. Sigma hat is a cone around the origin. Now, there's really not many possibilities for what sigma hat can be. We know that if we take the link, if we intersect it with S2, then we're going to get something which is minimal in S2 minus the two poles where the tangent line to gamma intersects. So this is minimal S2 minus the tangent line to gamma. So we look something like this. This is S2 minus the poles where T0 gamma hits, and sigma hat is something minimal and properly embedded in this space. So clearly it has to be comprised of geodesic arcs. One possibility is that you could have a great circle which misses both of these points. Something like this. But this leads to a contradiction. This we can rule out quite easily, because this is the tangent line to gamma. So if I draw a small loop which winds once around this, and remember that my sigma hat is a limit of the nodal sets of my rescaled sections U hat, then I know that U hat has to vanish on such a loop, right? Because it's a section of the bundle, and the bundle is defined so that any section has a zero on such a loop. Okay, but this picture is telling me that very far along the sequence, my zero set, which is the plane passing through this great circle, will be disjoint from this loop. So if I was in this setting, then eventually my sections would have to become non-zero. This is not allowed. Okay, so the link is not allowed to be a great circle, which misses both of the points. And the only other possibility is that it's a collection of half circles going from one point to the other. So, let me write that. So it looks something like this. Okay. Some number of half circles which connect these two poles. And what does this mean for sigma hat itself? Sigma hat is a collection of half planes meeting along a line. Right, so sigma hat consists of some number of half planes meeting along zero. And now all that's left to do is count them. We need to show that there's only one. Let's let n be the number of half planes. And we first consider the case that n is at least 3. So what does this mean? Which means that we have some number of half planes meeting along the line, and even if we spread them out as evenly as possible, there'll always be 2 of them where the angle between is less than 2 pi over 3, right? No, that's not right. It will always be less than pi over 2, yeah? So the worst case would be Two of them are very, very close together, right? But then both of these angles will still be strictly less than, or at least one of these angles will be strictly less than pi. That's what I want to say. How many times am I going to get the angle wrong? So, right, the angle between some pair of these almost pi. Strictly less. This we agree on. Sorry about that. Right, and what does this mean? This means that between any two such planes, we can drill a hole, which will decrease the total area of the configuration. So what I want to do is delete a piece here, and delete a piece here. And drill a hole. Okay. And as long as the angle is less than pi, and I make my tunnel thick enough, this will have strictly less area. Right, just because it's faster, it's shorter to go from here to here than it is to go. Yeah. And of course, I'm drawing this picture in cross section, but you have to imagine it in 3D. The tunnel that we're drawing, we have to make a hole here, a hole on the other side. Make a tunnel like that, and as long as it's chosen to be sufficiently large, this thing will have less area. And right, we're not done. We need to show that this leads to a contradiction. And the way to do it is, again, to remember this sigma hat is obtained as the limit of some minimizing sections. So there's one final construction to do, but it's straightforward, which is to show that from this competitor surface, which has less area, we can construct a competitor section which has less energy than U hat K. And this again is just done by, you take your surface, you look at a one-dimensional profile over the distance function to the surface, okay, and this will have energy close to the area of the surface after rescaling. But performing this kind of construction, you find a section with energy close to the area, and since the area is less, you must have decreased the energy when doing this. So what we do here is by drilling a hole, we find a section less energy. Which gives us a contradiction. Okay. So in fact, we can't have 3 or more half planes meeting. So what possibilities are left? The only possibility is that we have 2 or 1. Let's consider now the case that we have 2. And of course, if these are such that the angle between them is less than pi, then we can do the same thing as before, but that's not really important. But okay, the enemy would be 2 half planes meeting, forming an angle of pi. And then in this case, what does this mean? I think what this is saying is that for our original surface sigma, when we blow up at this boundary point, we see a plane. But that means that this point doesn't really lie on the boundary of sigma. Sigma will be a smooth embedded surface in a neighborhood. So somehow this piece of the boundary has been subsumed into the interior of sigma. In which case sigma is not really a solution to the Plateau problem in the sense that we want. So I suppose this case it's not a problem for the regularity, but it's a problem for sigma being a solution to the Plateau problem, which is what we want. So how do we rule this out? Well, now we do our usual trick of considering a loop which winds once around this piece of the boundary. Then remember that this sigma hat is a limit of the nodal sets. You have K. And so if the picture is really like this, then what we see is that along our loop, when K is very large, the section has exactly 2 zeros. If it has 2 zeros, then it can't close. Okay, so in other words, the topology of the bundle is such that sections should have an odd number of zeros, at least if they're non-degenerate. And this rules out the possibility that the zero set limits the
Can it be that star in the that you have to cross here? No, I mean star there in the middle and finish in the middle, but you have to cross at some point. You know, the level set is the middle line that you want.
Yeah. So yeah, that's right. So I guess there's one detail which I'm skipping over, which is we know that these zeros are non-degenerate because around this zero set you can do a blow-up argument which tells you that the profile actually looks like the one-dimensional solution. So the gradient of the section has a uniform lower bound at any zero. And so since the zeros are actually non-degenerate, there has to be an odd number of them. And yeah, so you could start in the middle and end at the middle, but it doesn't matter. There still has to be an odd number. Okay, so let's say this tells us that our section has an even number of zeros in the loop. But, this contributes. This contradicts the fact that our bundle restricted to the loop is the Mobius bundle. Okay, so we've ruled out n greater than or equal to 3. We've ruled out n equals 2. So the only remaining possibility is n equals 1, which means the tangent cone to our minimal surface sigma at any boundary point is a single half plane, which is what we need to deduce regularity. There's only one last thing which I should explain, which is why is this sigma a solution to the Plateau problem? So that means we have to prove that it has the least energy among all surfaces. Let's say sigma prime smooth with boundary and boundary gamma. Then if the area of sigma prime is less than the area of our surface sigma coming from the minimizing Allen-Cahn section, then this should lead to a contradiction. Okay, and how do we do this? Well, all we need to do is find a section whose energy approximates the area of sigma prime. I already explained how to do this in the beginning by passing through the double cover and doing a one-dimensional solution composed with a distance function. Right, so since the energy of our section U, this is converging to 2 sigma times the area of sigma. So for small epsilon, we get a contradiction. But energy of U is converging to 2 sigma of sigma, as epsilon goes to 0. So this contradicts U being minimized. that's all I want to say about this proof. So let me just finish by mentioning a couple of open questions. I've described how to prove boundary regularity by blowing up and applying the Allard regularity theorem. And then I've described how to get interior regularity, right, using the results of one way. Their results don't directly make use of the Allard regularity theorem for minimal hypersurfaces. Rather, they work directly with the nodal set of the solutions to the PDE, and they're able to use PDE techniques to prove curvature estimates directly. So I think it would be very interesting to know whether a similar sort of approach can be applied here. Can PDE techniques so that even before sending epsilon to 0, the zero set of that section is smooth up to the boundary? And if that's true, then likely one can prove some kind of curvature estimates which show that you also have smooth convergence up to the boundary. Prove C2 alpha convergence not in the complement of gamma, but in R3. That's it.
Thank you very much. So what are you feeling about this question?
It's hard. Somehow the first step, it seems, would be to take this half line or half plane in R3 solution, whose construction Marco described, and prove some kind of uniqueness theorems for this. You know, think about the minimal surface case. Somehow curvature estimates are equivalent to a Bernstein theorem.
Yes.
And there's a similar kind of analogy at play here.
So you should do that with boundary, the only solution.
So yeah, you would want to prove something like, first of all, in R2, if you take R2 minus the origin and look at the bundle over that, and take a section which is entire and minimizing or stable, show that it has to be the model solution whose zero set is half of a line. So yeah, this is a Bernstein type theorem.
It's like a Cabrera, this kind of thing, right?
Exactly. And
but we
in all of the interior, you know, curvature estimates for level sets,
even
somehow
you can think in something like Joaquin say that for in the minimal case, you have a line with you put a quadratic variable or quadratic energy variable.
Yeah.
So if that will be enough in this case, for example, if you have this model density formula.
Yeah, I mean, I guess the difficulty that we've been facing is that this half-line solution, it doesn't admit an easy characterization. Like the corresponding problem in the interior case is to prove classification results for the Tanch solution, and that has, you know, it's easy to characterize because it's one-dimensional. So if you can prove that the gradient of the solution always points in one direction, then it has to be the Tanch solution. And in fact, this is how most of the proofs
Yeah,
proceed.
because that's condition that is stable and then stable is the one.
The stability you can assume, but then you need some way to show, okay, if my solution satisfies such and such condition, then it has to be the model. And so there's what I want to say is, apart from stability, there's many properties which characterize the Tange solution. It has flat level sets. Maybe that's the best one to think about.
What's the property of the model solution?
Yeah, we don't have anything like this, right? The level sets are not flat. It's not rotationally symmetric, or it doesn't have any kind of obvious symmetry which you can exploit.
No symmetry at all?
I mean, I don't think so. No. So, yeah, so you see it's not clear how to characterize it. But that would be the first step to doing this kind of regularity at the level of the nodal set. And then, yeah, but even if you have that, I think it's still a hard problem to get these estimates.
Thank you, Stephen.